So last time we stopped at linear combination of vectors. Why do we need this for? Why do we need the linear combination? What's your guess based on the things you already know? Why do you think I introduced linear combination of vectors? Where am I going with it?
Coordinate systems?
In the right direction, but what in coordinate systems? What am I going towards to? Basis, right? Probably that's what you were thinking about. So today, what I like to do is basically develop the idea of basis, and then we kind of leave the vector to introduce tensor. So let's look at the linear combination again. I write it again for warm up. So we imagine that we have a given vector space. We used this symbol last time, and we consider vectors v1, v2, all the way to vm, which belong to the vector space. So imagine that we also have a set of numbers such that this linear combination, this is v1, sorry, v2, vm is equal to 0. Tell me, is this a 0 vector or a 0 number? Vector, right? So I need to put this underline to distinguish that from a number. So imagine that we have these vectors given, and we have this linear combination equal to 0. For unknown, this is kind of an essential term here. Real numbers which belong to the set of real numbers R, which you have seen last time. So if we have this linear combination equal to 0, can you think of a solution to this equation? Something very simple. All alphas equal to 0, right? All alphas equal to 0. I don't want you to make you feel bad for those of you who gave the right answer, but this is called the trivial solution. So the trivial solution is, you all can see, all these alphas are equal to 0. And this is a 0 number. Now, what if the trivial solution is the only solution? If you don't have any, if you search for any other number combination and you don't find anything else, if this is the only solution, what do we call these vector, these collection of vectors, this subset of vector space? They are linearly independent. So these vectors become interesting if this is the only solution. So let's just write it so we have it written. So if the trivial solution is the only solution, and the word only is important here, we say V1, V2, Vm are linearly independent. And that's the fancy term to say that you cannot write one as a linear combination of the other. That's what it means. So they are linearly independent. You can take one of them and write it as a linear combination of the other ones. So why do we care about that? Remember, I want to go towards basis. This is important to make the definition for a basis for a vector space. So I start by telling you something that you may have heard in some other ways, but I just write a sentence and then we discuss what it means. So it turns out that the largest number of linearly independent subsets of any vector space V is, I use the word bounded. What am I saying here? I'm saying that if I have a vector space, I have no idea what it is. I take some vectors and then I take two vectors which turn out to be linearly independent. I look at three vectors linearly independent. I go up. At some point, I hit a wall. There is a bound for the number of vectors that are linearly independent inside a vector space. What is this bound? Any ideas?
Dimension.
It is a dimension of this vector space. So this is the formal definition of dimension of a vector space. So we call this bound basically is the dimension of the vector space. And we care about it because this is exactly what we need to define a basis. So now we come to, actually we were making all these introductions to actually get to basis. So a formal definition of basis is that basically it is a linear independent subset with the maximum number of vectors that you can have in that vector space. So if you reach that wall, that subset would serve as a basis for the vector space. So let's just write it down. So a maximal linearly independent subset is called a basis. Things will start become more interesting now. We have a basis. So why do we need a basis for? I was talking about vectors before and then I switched to basis. Why? What have you used basis for before in your life? I'm sure you have seen basis before. Do you need it to define a vector?
Not to define. Tell about the directions when you need a reference frame.
We are not talking about coordinate systems. You are saying the right thing. I'm just looking for some different words. So the vector is somewhere in the space, okay? You want to somewhat represent it. So you need to define a basis to be able to represent a vector. I think Prabha was saying the same thing. But we are not talking about coordinate systems yet. I haven't even told you anything about coordinate systems. We are in the space, okay? There is just a space, some basis, a vector. So a basis, we needed to represent a vector. So let's see how would we do that, and what type of basis would suit us the best. What would be the easiest, the best kind of basis we can use. The basis, we also use uppercase script letters. This is also the notation in the book, so I'm following the same thing. So for example, I start with a basis. I call it G. This is how I write the So what is the dimension of this vector space then? N, right? Immediately you should see that. For every vector which is inside the vector space, we can basically represent it uniquely in terms of these basis vectors. So there exists a set of unique let's say n unique scalars such that, as you told me yourself, you can basically write U as a linear combination of these unique scalars and the vectors in the basis. So here we are. So these are the scalars, and again remember that they are unique. I write this in a summation form again here in this next page. It's the same thing. Now, what have you called these scalars before in other classes, courses, in your life in general? Components, exactly. So these are components. Components of vector U. Does U have just one set of components? I said U1 to UN, this is a unique set of numbers, but I shouldn't have used the word but does U have just one set of components? No. So we need to make this a little bit more, state this a little bit carefully. These are components relative to the base I chose, relative to basis that I chose earlier. This is somewhat, I should have made this red actually, because this is important. The vector doesn't change. The vector doesn't care what basis we are choosing. What is changing is the components. So vector is invariant to the basis we are choosing, but the components are going to change. Another point is a vector space. How many bases do you think there are in a vector space? No? I thought you wanted to say something. How many bases can you define in a vector space of dimension n? Infinitely many. You can define many. Just take one, rotate it, do whatever. What is common between all of them is that they all will have n number of elements, n number of members. So that would be the common thing between them. Now, before going forward, I need to define or remind you, you already know, of inner product of vectors. What is another name for that? Exactly. You probably see where I'm going. Let's just define it. So if we have two vectors that are in this vector space, the dot product is defined as, so we can use this symbol for definition. Hopefully you still remember. So we have the magnitude of the first vector, magnitude of the second vector, times the cosine of the angle between the two. So if I make a small sketch here, this is the smaller angle between the two. You all know that. What's the product? What kind of output is it? We give in two vectors, what do we get back? Yeah, everyone knows that, so that's great. So we all know that. What happens if a dot product is equal to 0? Exactly. Just checking. So sometimes we use the word perpendicular. For some reasons that you will see in a second, I use the word orthogonal. Just the same thing. Now, that brings me to the definition of orthonormal basis. So let's consider a basis. And pay attention that I'm going now to use a little bit different, slightly different notations here. Before I used G1 through Gn, now I'm using some funny looking with a hat on elements. If it is in n-dimensional, I always have n. So, what makes these spaces orthonormal? what conditions these vectors should satisfy for these spaces to be orthonormal. Yeah, so exactly. The way to write this from now on, the same thing you said, I'm just writing it in a different notation. Looking at the survey, I think the class is heterogeneous in terms of how much you remember from index notation or you have seen. So just what you said, you can write it like that. Using this symbol, which is called? Perfect. And I guess this is a very useful, it's like a switch. It's either 1 or 0. If I and j are equal, 1, they are not equal, 0. Now, this will be the definition of orthonormal bases. So pay attention that each one of these vectors, the magnitude is 1. And they are mutually perpendicular, orthogonal. This is, you guys know that. Why do we like so much orthonormal bases? Now, going back, I was talking about bases. I talked to you about components. I showed you that you can write a vector in terms of components. And then I said, well, it looks like there are some special kind of bases called orthonormal bases. Now, why do we like them so much? I'm sorry. Or you can use a normal basis for that. Doesn't need to be orthonormal, right? Yes, that's the point. Easy. Orthonormal bases make it easy. They make everything easy for us in terms of how we represent the vectors. And how we get the components. So I just go to that directly. So if G is orthonormal, then if you have a vector, like before, you can write the vector as the summation like that. What is easy if this is orthonormal is how you get the components. How do I get the components? If I just get the vector and I use the dot product, which I just introduced a few minutes ago, with the ith element in the basis, then I'm going to get the ith component. So that is why we like orthonormal bases so much, because dot product is easy. So if you can get the component just doing this dot product, why not? This would be a very good thing to do. So before moving towards definition of tensor, let's just remind ourselves also, I kind of put a line here. And now that we talked about inner product, let's also talk about cross product. because we need it in a few minutes. So, I hope you remember the cross product as well as you remember the dot product. First of all, tell me, can I define cross product in 2D, 4D? Cross product is only defined in 3D. So that's one thing to remember. And what is the product? What is the output? So unlike inner product, the output is also a vector, right? I know you know that, so I'm going to just go through it very fast. So we have a vector, we have to define its magnitude. Try not to look and see if you can write it yourself. And then just check. No? It's too late in the afternoon. Forget about it. What else do we know? This is not enough, just the magnitude. This is not a scalar. What else do we know about cross product? The direction. I tried to use my best artistic abilities to draw that. So you probably remember that there is the right-hand rule. So if you go from U to V, the direction perpendicular to the plane, which is contains U and V, is the direction of W. So it gives both the direction and also, I mean, you can see, if you are left, is there anyone who is left-handed? One? Sorry. So there is, I don't know if you have looked at the statistics, 11% of people are left-handed. So I don't know, there should have been 2 people in this class. If someone is hiding, it's okay to be left-handed. Yeah, there seems to be a whole like group of people who are left-handed, and if you look online, you see a lot of conspiracy theories about why being left-handed is smarter or not. You see statistics on presidents who have been left-handed. It's amazing, and I know that because my husband is left-handed. So we have these discussions for anyway. Just was a joke that you feel less tired. So we know everything about now vectors. What I want you to know in this class, so we can start building up towards definition of tensor. I start with, you will see why, but I have to start not with tensor. I start with the definition of functions. So I start with the definition of a scalar valued functions of vectors. So last time I showed you a function, it was distance. So we kind of use this notation. Function is mapping basically a vector. So it's mapping the vector space into the set of real numbers. Do you have an example, a physical example of such a function? Temperature. That was almost too fast, Prabha. So tell me now, that's great, temperature. So temperature, what is mapping, what is it mapping what into what? Temperature as a function of position, exactly. So it takes the position vector, which is a vector, it gives you temperature. just because I think all of us, or most of us, are engineers, so all of us are scientists or engineers, so it's good sometimes to have some physical face for whatever we are talking about. Now, what is important for us in this class is linear functions. I should have used another color for that title, but that's fine. So, I just write the definition and we do some examples to make it clear. So f is a linear function if you input a linear combination. Remember linear combination? We defined it earlier today, of two vectors or more. I'm just writing two. So if you input a linear combination, the output would be the linear combinations of outputs with the same coefficients. Let me write it, then it's very clear. And this should hold for every scalar in the real space, and also for every vector in the vector space. So if you input a linear combination of vectors, the output would be a linear combination of the action of function on those same vectors using the same coefficients. That sounds very wordy, but when you look at it, it's clear what it is. Now let's jump into examples which helps you also kind of not feeling tired. So I define a vector, a function z such that it maps every vector that it gets into 0. The question is if this is a linear function or not. This is number 0. I should have used my usual 0 number. So when we want to investigate whether a function is linear or not, this one I'll do it, the next one I'll let you to work on it. So all we have to do is we have to say, okay, if we take two vectors v and w and apply and kind of act this function upon them, can we say that this holds? Here is kind of very easy, right? The linear combination of vectors is also a vector, right? So z takes any vector, brings it to 0. So left-hand side is simply 0. Right-hand side is also alpha times 0 plus beta times 0. So for any alpha and beta, this is also 0. So yes, what is important is that this has to hold for every vector in vector space and for every constant or a scalar alpha and beta. So we say yes. Z is a linear function. So the next example, I let you write it. So if we have an orthonormal basis, then we define a function that it takes a vector in vector space and it maps it to its component. And let me remind you here, just that you see this many times, that the component then, we said it's easy, right? Orthonormal is easy. I forget to switch colors. Is this a linear function or not? So that you do something on your own and kind of wake up. Just try to just write it down yourself and show to yourself that it is okay. So is it linear or not? It is linear, right? So if I take on the left hand side, and you can easily see that this is the case. You may have used the dot product to convince yourself, but however you do it, it's very easy to see that this holds. And important is that this holds for every U and V and every alpha and beta. You can use the dot product, and just to save time, I'm skipping that part. I think this is the last. The last example is again a function. So a scalar valued function of a vector. And the definition is this time that it takes a vector and the output is the magnitude. Is this a linear function or not? No. So to show no, the best way is to really write it down. Try to prove that this is not the case. Just write at least the formulation that what you have to have for it to be a linear function. If you see it immediately, that's fine. It's important that you kind of remember what to do. Sorry. So the left-hand side would be the magnitude of, did I use V and W, I think, yeah. Right. And this is obviously not true. As you know, the magnitude of a vector, you can use the dot product. Now that we talked about dot product, I can just use it. Right? So this is not a linear function of u. So the answer is no. G is not linear. So I introduced the linearity of a function because we are going to need it to define a tensor. So the last thing about the scalar valued functions of a vector is a theorem which we don't prove, but we just state here. So if f is a linear function, sometimes this is called a linear form or a linear functional. There exists a unique vector u sub f, so f referring to f, such that I forget to change colors all the time. What does it say? If you have a linear function, the action of the function can be represented by a dot product. There is a unique vector that you can find that you can represent the action of the function in the form of dot product. So let's quickly look at the very simple examples we had before, the two ones which were actually linear, and see if we can kind of very quickly decide which vector is this u sub f, this mysterious unique u sub f. So if we go back and look at example number 1, let me remind you, this was the real simple what is u sub f in this case? I mean, would be u sub z. What is this vector here? So basically what this theorem says is that this function, you can write this function, the operation, as an inner product of some vector and the argument vector v. What is the vector here? Yeah, this is very simple, right? If you take a zero vector, then this is the case. It's basically to show you what this theorem exactly means. The second example that we did was something like that. It was a functional which would take a vector to its ith component, right? So now if I want to apply this theorem, what is the mysterious unique, in this case u sub f? Exactly. Right? So it's kind of a fun theorem. Now, this was a scalar valued function of a vector. To define tensor, what we need is a vector valued function of a vector. So I'm giving you all this introduction to get there. So let's define that. Maybe I go to the next page. Okay, so next I want to so that is when the function takes a vector and gives back a vector. Physical examples. Oh, you seem to be full of examples today. What is x? Flex. Okay, so what is the first vector and it is mapped to which vector? Let's be in the realm of elasticity, right? We are in elasticity. So again, if you want to give me an example, tell me that moment is a function of force. So as a function of force, that is a good example. What else? Traction as a function of But traction is kind of a force. Oh, okay. That's a good example too. So you can also think of, the simpler examples would have been just force as a function of position, displacement as a function of position. So kind of this is typically what we are seeing in elasticity. So you are thinking about more complex, but this is obvious to you what it means when we talk about a vector valued function of a vector. So now let's jump into examples. I guess you all know what it is. So one example is, I call this function I, and this is, now it's mapping vector space into vector space, such that this is a vector function of a vector. Have you seen this before? No? I'm sure you have. Yes, it's the identity. Yeah, it's the function. So we are building it up. Don't worry if you think you haven't seen it. Maybe you haven't seen it in this form. So it's taking a function, a vector, and it gives you the same vector back. Think about linear algebra, identity matrix, for example. What does it do? You have the same vector. If you put a vector and you multiply it by identity matrix, you are going to get the same vector. I'm not saying that this is a matrix. I'm saying that's the idea. That's why this is. This should remind you of identity function. We call it for now function. I haven't given it any name or anything. So another example parallel to what you had seen before is a function that takes one vector in the vector space, and instead of a zero number, it maps it into a zero vector. This is a vector valued function of a vector. Another example is some of them I'm writing them more formally than the others. We are engineers, so I allow myself not to be always mathematically. So it's going from it's G sub u such that, so G sub u in this case is defined as so it takes u and cross product of u with v. So that's a particular u. For every vector in vector space, it cross products that u with that v. And we talked about cross product. So when I think Roy mentioned momentum, right? So momentum, if you remember, you basically cross product position and force, right? That could be an example of that. You are taking one vector, you are cross producting, getting another vector. It's a function. Moments. Yes, I'm sorry, I said momentum. Please always correct me. Sometimes I think, yeah, I'm thinking something, but I say something else. So always correct me. And of course, this is not a mistake I make. I just want to make sure that you are paying attention. It's not true. Okay. So now the question is if this is linear. Try to see if this is linear, so you are kind of engaged, so you don't fall asleep just listening to me. This is late in the afternoon. I'm very concerned about the energy in this, the sum of energy in this class. Try to see whether this is a linear function. So I write it quietly without saying anything. You work on it and you check just looking back. How about that? Gerald, question. So it is linear. Why could I easily go from line 1 in the solution, so from here basically to here? Cross product is distributive, right? Yeah. You can we can do that. Just wanted to make sure that you paid attention. Okay, so now all the kind of introduction comes to the point where we define a tensor properly. So what is a tensor? Before I define it, problem. Sure. Exactly. So I built up all these introductions to tell you that a tensor is actually a linear function of a vector mapping a vector to a vector. So it is a linear vector valued function of a vector. So since this is important, we write it down. So for those of you who don't, what happened here? No, it's not. So if you take classes in math, probably this is, they would, if you define it like that, some people can get very upset and say, you know, that. So this holds for the tensors that we need in elasticity in most applications, especially for second order tensors that we use the most. But it is not the comprehensive definition of all tensors. So no, I will not try to define things. I don't know why, but I have some technical problems. Okay. It seems that the performance of my surface is also time dependent as we go towards the it's like, I'm getting tired. So a tensor and I kind of can put it here, especially a second order tensor is a linear, so that's why we were talking about linear functions. Function I just write it like that. I think we are all now familiar. Why do we care about tensors? What are the physical quantities that are in the form of a tensor? A stress, a strain. So those are good examples of tensors. So examples are a stress tensor, strain tensors. And I put here an asterisk that remind you of the point your friend just made. This is not an overall general definition, but that's good enough for us in elasticity. Now, when you consider a tensor, it's important, you know how I asked you when you are talking about a vector valued function of a vector, which vector is going to which vector? When you are thinking about tensors later on in the class, I want you to remember this definition, and I want you to think what vector is being mapped into what vector. Like, what are you exactly mapping when you are looking at a stress tensor, a strain tensor, etc. So that's why it is important. So now we need to define some new forms of vector products to be able to mathematically describe tensors. How many of you have never seen tensors before or tensor products? Okay, great. So you all have seen it at some point. So I need to define what is called a tensor product or an outer product. So if we pick two vectors, A and B, we use this notation to write what is called a tensor product or an outer product. So this is defined as, this product is defined as follows. The action of A tensor B on a vector, so this is a vector, that's a tensor, is equal to B dot C. That's a dot product, gives you a scalar, times A. On both sides we have vectors. The action of a tensor on a vector is a vector. We said we go from vector space to vector space. And then you have a scalar multiplied by a vector, which is also a vector. So the question is this a linear? Okay, that was interesting. Is this a linear operation? And the answer is yes, and you can verify it on your own. So now, this is important. So this equality here is important. Now that we have these definitions, we can start talking about the components of a tensor. So if we have a tensor, T, we know that it's a linear mapping from vector space to vector space. We denote tensors in this class with double lines and instead of writing T times V, we just, the action of the tensor on a vector, we just write it like that. So this is basically, it's saying that tensor T is acting on vector V. That's what it is saying. Okay. And then we come to the very important thing. We can show that if you have an orthonormal basis, any tensor T in that basis can be represented using the outer product that I just introduced. So we have a double summation on I and j ranging from 1 to n, and then the component of the tensor I show T I j and then EI tensor EJ, or the outer product of EI EJ. Now, it is useful if this is to kind of, in the back of your mind, to compare this. For example, I just put it inside the cloud. So for vectors, we write a vector in terms of the components and an orthonormal basis like that. For tensor, this looks like this. And that's super important. The component ij we can get by dot product of ei, then the action of tensor and ej, which we said we write it like this. We are going to see a lot of this. Is Tij a scalar, a vector, or a tensor? It's just a scalar, right? And on the other side is also a scalar, so we are all good. Two vectors dot product. And kind of, I guess we are over time, but just that you kind of in your mind, you compare this to, when we said a component of a vector was just a dot product. For a tensor, you have a summation. You have also a dot product. Kind of to have this analogy with the vector. If you want to read this outer product, you can say like EI outer product EJ, or you can say EI tensor EJ. This is what is accepted. Okay, I guess we need to stop. So see you on Tuesday.